Okay, so now I'm going to correct myself. So I was asked about the outliers last class, and I do not remember who, but I know someone asked me, and they were asking, oh, like it says potential outliers, but are they actually outliers? And I said no. Um, I usually read through the textbook and fill in these notes. And in the textbook, they only ever call them potential outliers. But then I was going through the material that like the course coordinator for the class has given me, and I realized that we are going to say they are outliers for sure. So I apologize because I answered that question wrong. So yes, whatever you identify using the 1.5 times the IQR criterion, we are going to consider them outliers. That was the biggest mistake that I made, and that affected my box because of that. So yes, they are outliers. I'm really sorry that I said no, because I know that's probably confusing. They say potential, but they are actually outliers. So just to clarify. And then that affects my plot. So this is where I made the mistake because I didn't consider 62 an outlier, even though we identified it as one. And if you go up in our notes, when we first introduced the plots, it tells you to indicate outliers by a little star on your plot. And I did not do that because I didn't consider 62 an outlier. So I just need to show you guys how to fix that. Because like I said, you do need to know how to do this correctly on the exam, and that's my bad. So if you come down here to the box plot, this is where I made the mistake. So I'm going to erase my whiskers here. Well, just the right one. The right one's the only one that's got an issue, so it should say 15. Okay, so any outliers that you identify using that criterion, you indicate with a star. So instead of having my whisker extend to a 62, I should have just put a star at 62 because it's an outlier. So that was the biggest problem that I made. And then you're probably asking, okay, well then where do I draw like the other whisker to? So if you come up to where we ordered our data, since we're considering 62 an outlier, we're going to draw the whisker to the next like highest point. So the whisker is only going to extend to 38 instead of 62. So if we come down here, now this should only extend to about 38. And that is the correct box plot here. So that was the mistake that I made, was I did not identify 62 as an outlier on the plot. So anything you identify as an outlier, you just need to put a star and then put the value above it. And then when you draw your whiskers, you would just draw it to like either the next highest one or the next lowest one instead. So that's the big problem. So I just want to clarify that that's the correct way to do it. So use this as an example in your studying. Once again, I apologize because I know that's super confusing, but hopefully that clears things up. Okay, any questions on that before I move back to chapter 4 now? Okay, sweet. Thank you guys for being understanding because that was a yikes moment. Okay. Save this. Okay, I'm gonna come to this. So we're back to chapter 4 now. Okay, and I remember we ended with doing these tree diagrams, and I said, why don't you all try this one at home and see if you can get it. It's like a little hard to draw. I don't know if anyone else felt like this was a lot to draw for a tree diagram, but having 5 shirts like made it super big, and like, oh my gosh, it was just like hard for me to at least draw in this small area. So I have like a little key for the notes. So I'm just going to show you all what the correct version should look like, because I don't want to take the time to draw this thing again. Okay, so this was my tree diagram here. So I started with, first of all, choosing a shirt. So for shirts, I just use S's. So S1, S2, S3, S4, and S5. And then for each shirt, you can pick a pair of jeans, and you can pick J1, J2, J3. Then I had to do that as my next one. And then for each pair of jeans, you can pick one of the 2 hats. My goodness, this is a big tree diagram. Like, I had to write really tiny. So if you want to take a screenshot of this, feel free to, because like I said, I didn't want to take the time to rewrite this whole thing. And then I also didn't write the whole sample space out because I figured if I got it started, you all could probably finish it. So The first thing in my sample space is going to be if I pick shirt 1, jeans 1, and hat 1. And so that's S1, J1, H1. And then my next thing would be if I picked shirt 1, jeans 1, and hat 2. That would be the next one. And you can see that I just worked my way through all the possible branches. And if you just continued that down, you should get all of the possible options. So you should get the whole sample space. There should be 30 things in your sample space. So if you want to make sure that you did it correctly, you should have 30 different options. So, okay, next I will move on to our next thing. Okay. All right, so the next thing that we're talking about is some definitions. So first of all, an event. So let's define what an event is. And remember, we're just doing some basic probability definitions because we need to have these vocabulary words before we get into different types of probability. Today will be very probability oriented. That's literally all that we're doing. So hopefully everyone's okay. Probability can be a lot. There's a lot of little rules. So just so you know, that's what we're doing today. So anyways, an event consists of a set of outcomes of a probability experiment. So an example would be rolling a die and getting a 6. So that would be a possible event. So an event would be, okay, if I rolled my die and I got a 6. And that's what's referred to as a simple event. And the reason that it's called a simple event is because it's an event with one outcome. What I mean by that is the only like outcome is getting a 6. That's the only thing that makes this event like true is if you roll a 6. So there's one way to satisfy this. And then another example would be this one below where it's rolling a die and getting an even number. And this is what's called a compound event. And the reason why it's called a compound event is because there's multiple ways for this event to happen. So to roll an even number, you can roll either a 2, a 4, or a 6. So you can roll any of those options and that event has taken place. So it's called a compound event because ideally it consists of more than one simple event. So this consists of 3 simple events. So simple event, there's one thing that can happen for that event to be, true and take place. And then a compound event would be there's multiple ways for it to. So with rolling a dice, if it's an even number, you could have that happen 3 different ways. You could roll a 2, a 4, or a 6, and that satisfies that. So that's a compound event. So it's really 3 simple events kind of put together. Okay. So now that we've got some basic definitions out of the way, we're going to get into our different types of probability. So our first one that we're going to talk about is theoretical probability. But before I do that, let me just say that there was a typo on the notes, and I realized it today, that this should be empirical. Just wanted to tell everyone there was a typo on the first page because I realized it as I was prepping my lecture. Okay. So anyways, first though, we're going to talk about theoretical or classical probability. Okay, and this is defined as probability that uses sample spaces to determine the numerical probability that an event will happen. So key thing is that it uses sample spaces. And we've been doing stuff with sample spaces and talking about the sample space if you roll a die is 1 through 6. If you flip a coin, it's heads or tails. So theoretical probability will use your sample space to determine the actual probability that something happens. This will probably make more sense when we do an example, but let's talk about a few details with theoretical probability. So we do not actually perform the experiment to determine theoretical probability, hence the name theoretical. We don't actually have to perform an experiment. So if you're saying like, oh, what's the chance that I roll a 4 if I roll a die once, you're not actually doing anything. You're just using the concept that there are 6 possible outcomes when you roll a die, and so we'll just assume they're all equally likely and tell you that, oh, there's a 1/6 chance that you roll a 4. You don't actually do anything. So we'll get to a part of probability where you actually conduct a form of experiment and then you use that data to give a probability. But in theoretical, you don't actually conduct an experiment or do anything. You just use in theory what we believe to be accurate. So the next bullet point says that it assumes all the outcomes are equally likely to occur. So like I said, with rolling a die, we assume that you have an equal chance of getting a 1, 2, 3, 4, 5, or 6. That's just the assumption, is that they are all equally likely to land when you roll a die. Same with heads or tails. We would assume that there's a half chance you get a heads, half chance you get a tails. Okay, so those are some things about theoretical probability that distinguishes it from other types. So all events are equally likely to occur. And then now we actually define below how we find the probability. So you see this part here that says P of E. So this P parentheses E, this is read or understood to be the probability of event E. That's what that means. So if you see P of E, that just means the probability that E happens. So P of E is defined to be the number of possible ways to get E over the number of outcomes in the sample space. So we will do some examples, and I think that'll make more sense once you practice it. But first of all, let's talk about some rounding rules and probabilities. So probabilities should be expressed as reduced fractions or rounded to 2 to 3 decimal places. If the probability is extremely small, then you would round to the first non-zero digit after the decimal place. So usually I prefer fractions for probabilities if it's not too difficult to keep them in fraction form. I don't mind decimals, but yeah, like this says, either small fractions or reduced fractions, or decimals with 2 to 3 decimal places. So not like huge decimals. You can definitely round it to just be 2 decimal places or 3. You'll see some questions where it seems like it's easier to leave it as a fraction, or where it would be easier to make it a decimal. Okay, so let's do some examples here. So consider a deck of cards. So the first question is, find the probability of selecting a queen. So if you pick one card out of a deck, what's the probability that you would pick a queen? So as you can see, like we talked about, this is written as P queen. So this is the probability that you select a queen. So the way that we've defined this is the numerator is the number of ways to get E. So in our case, we have to ask ourselves, how many ways, or what's the number of options for us picking a queen? Okay, well, how many queens are in a deck? Anyone know?
4.
Perfect. Yes. Thank you. There are 4 queens in a deck of cards. So your numerator, so the number of ways to get a queen would be, oh, that's a highlighter. Sorry. Would be 4. There are 4 queens in a deck. And then the denominator is the number of outcomes in the sample space. So this just means how many cards are there in the deck. And we did this last time and said there were 52 cards. So there are 52 cards in the deck. So your answer for this is simply just 4 over 52. Because there are 4 ways that you could draw a queen, and there are 52 possible outcomes. So if I draw one card out of the deck, there are 52 possible things I could draw. But 4 of them are queens. So there's a 4 out of 52 chance that I pull a queen out. I will say, please reduce your fractions. So this reduces to 1 over 13. I will mark you down if the fractions are not reduced, just because that's important. So please, please, please reduce. So in a situation like this makes the most sense to probably leave it as a fraction. If you were to put a decimal, I'm not going to mark you off unless I specifically asked you to leave it as a fraction. But this would just make the most sense to leave it as a fraction because it's a pretty simple one. Okay, let's do question 2. So this is the probability of selecting a spade. So P of spade. So the first thing we need to ask ourselves is what's the number of ways that we can get a spade? So how many spades are in a deck of cards?
13.
Thank you. There are 13 spades in a deck. And then just like the last one, there are 52 cards in the deck. So this is going to be 13 over 52, which is going to reduce to 1/4. So if I pick a card at random out of the deck, I have a 1/4 chance at drawing a spade, which does make sense because there are 4 suits in a deck. And so if I just want a spade, 1/4 makes sense. Okay, our last one is the probability of selecting an ace of diamonds. So we have P of ace of diamonds, and this one is slightly different because there's only one way to get an ace of diamonds. So there's only one ace of diamonds in the whole deck. So that really limits that down. So there's one ace diamonds, and still we have 52 possible outcomes. So this probability is just 1/52. Because if I draw a card at random, I have a 1/52 chance of pulling out the ace of diamonds. So a pretty small chance. Okay, any questions on theoretical probability or those calculations and the number of ways to get it over the number of possible outcomes? Okay. Like I said, the deck of cards is a pretty standard example, or the rolling the dice, or the flipping the coin. All pretty common ones that you should be familiar with the sample spaces for. Those are ones I recommend knowing. Okay, so let's get into some rules. Obviously, we're going to have rules for probability or some facts for you. So the first rule of probability is that the probability of any event is a number between 0 and 1. So if you look at all the things that we've calculated up above, 1/13, 1/4, 1/52, those are all numbers between 0 and 1. So that's the first rule. So the probability of any event E is a number between, and I'm going to write a number between and including 0 and 1. So that just means that it could be 0 or 1. So it doesn't just have to fall between 0 or 1, it could be 0 or 1 itself. And I'll explain that a little more because that's some of the next rules that are coming up. And then I'm going to write in other words because there's a little interval notation way to write it. So in other words, the probability of E falls between 0 and 1. That's a little more mathematical way to say it. So the probability of E is greater than or equal to 0 and also less than or equal to 1. Okay, and that makes sense because like a lot of the times when you hear probability, you'll hear, oh, there's a this % chance of that happening. Well, that's a decimal between 0 and 1. So, all right, our next rule is that the sum of the probabilities of all the outcomes in a sample space is always 1. So the sum of the probabilities of all the outcomes in a sample space is 1. Now let's just think about this for a second and why this makes sense. So if you roll a die, or actually let's do a coin, this will be easier. So if you flip a coin, there's a 1/2 chance you get heads and a 1/2 chance you get tails. The only two possible outcomes for flipping a coin are heads or tails. So if you add together 1/2, the probability you get heads, with 1/2 the probability you get tails, you get 1. And that's that. So you summed up all the probabilities of the possible outcomes and you get 1. Same with rolling a die. There's 6 possible outcomes. The probability of each is 1/6. If you add those all together, you will get 1. Okay, the third one is if an event E can't occur. So in other words, the event contains no members, and I'll explain this more, in the sample space. Its probability is 0. Okay, so we said that you could have a probability that equals 0. So let's think of an example of this. So if you're rolling a die and I asked you, what's the probability that you roll a 7? You're going to tell me 0 because there's no 7 on that dice. So that's an example of something where the probability is 0. It's usually kind of silly stuff like that that doesn't really make a whole lot of sense. But yeah, if I asked you what's the probability you roll an 8, 0. There's literally 0 chance that you can roll an 8 with a die. So that's an example. Lastly, if an event E is certain, then the probability is 1. So this is just kind of like the opposite of rule number 3. So if something is certain to happen, you would say it has a probability of 1. So if you are rolling a die and I say, what's the probability you get a number 1 through 6? That would be 1, because you will roll something 1 through 6. Or if you're flipping a coin and I say, what's the probability that you get heads or tails? 1. You will get heads or tails. So those are the two ends of the spectrum where it's impossible for it to happen, so it would be a 0, or it's most certain to happen and it will be a probability of 1. Right, so those are our probability rules. And then next we get into something called complementary events. So the complement of an event E is the set of outcomes in the sample space that are not included in the outcomes of event E. So the complement of E is denoted by this E with a bar over top, which we read as, surprise, E bar. So the complement of E is denoted by E bar, and it is the set of outcomes in the sample space that are not included in the outcomes of event E. So I'm going to draw a little Venn diagram that might help with like a visual for this. So let me go ahead and draw. Okay. So let's say that my square here represents my sample space for rolling a die. You're going to be sick of me saying rolling a die after today. So let's say this square represents rolling a die. Let's say my event E is rolling a 2. So I'm going to say this event here, which it's just this circle. E is rolling a 2. So that's the event I care about. So E bar, or the complement of E, is everything that's not included in this event. So I'm going to say everything else that's in this square, or my sample space, E bar, is going to be rolling a 1, 3, 4, 5, or 6. So the complement of E is just everything that's not E, essentially, that's possible. So if I say my event E is getting heads when I flip a coin, E complement would be getting tails. It's everything that's not that event, essentially. Or if my event E was rolling a 1 or a 2, E bar or E complement would be rolling 3, 4, 5, or 6. So you can kind of think of it almost as like the opposite in a sense, or just everything that's not E. And the reason it's called the complement is because E and its complement together make up the whole sample space. So that's a little visual of what that means to be a complement of something. And I think we have some examples. Yeah, we have some examples with using complements. So right here, what is the complement of rolling a die and getting a multiple of 3? So let's think. Getting a multiple of 3 would mean that we either roll a 3 or a 6. So my event E, which is rolling a multiple of 3, would be rolling a 3 or a 6. Okay, well, E complement would be everything that's not a 3 or a 6. So E bar would be rolling a 1, 2, 4, or 5. Everything that's not E. And you'll see below why this is helpful for us when we calculate probabilities, when we do a little example below. But then there's this note here, which I kind of already touched on, but the outcomes of an event and the outcomes of the complement make up the entire sample space. So notice with my event of rolling a multiple of 3, that's 3 and 6, and its complement is 1, 2, 4, and 5. And if I put those together, I get the whole sample space. I get all 1 through 6. Okay, so next we talk about this rule for complementary events, and then we'll apply it, and you'll see why it's helpful. So the probability of the complement of E, or E bar, is equal to 1 minus the probability of E. You can also think about this as the probability of E bar plus the probability of E is equal to 1. Okay, so let's see why this is useful. So our example is the probability of purchasing a defective light bulb is 12%. What is the probability of not purchasing a defective light bulb? Okay, keyword not. So it's basically the opposite of purchasing a defective light bulb. So if you know that the probability of purchasing this defective one is 12%, let's say that that's my event E, is purchasing a defective light. And we know that the probability of E happening is 12%, which translates into just 0.12. And we want the probability of not purchasing a defective light bulb. So we want the probability of E complement. So we want P of E complement here. That's the opposite of purchasing a defective light bulb. Okay, well, our rule for complementary events says all we need to do is subtract the probability of E from 1. So this is equal to 1 minus the probability of E, which we already know is 0.12. And 1 minus 0.12 is going to give you 0.88, or 88%. So if I know the probability of an event, but I want the probability of its complement happening, you just have to take 1 and subtract the probability of the event. Okay, so I think I'm going to let you try this example on your own. So this is, what is the probability of not selecting a club in a deck of cards? So you want, you know what, actually, I'm just gonna let you guys go for it. So without starting it, I'm gonna let you all try this example. Once you get it, why don't you send me a private chat on Zoom with the answer that you got, and then we'll talk about it. I didn't even realize that those weren't private chats and you guys said something. That's fine. Okay, spoiler alert, the answer is 75% or 0.75 or 3/4. Okay, cool. Well, I'm glad everyone's getting the hang of it, so that's fine. I was really confused what you guys were saying, my bad, because they were correct. But okay, so let's just write this out. So we know the probability of getting a club is going to be 13 over 52 or 1/4. And then we want the probability of not selecting a club, or the complement of selecting a club, which is 1 minus 1/4, which is 3/4 or 75% or 0.75. I'm okay with any three forms as long as I don't ask you for a specific one. So I'm okay with fractions, I'm okay with decimals as long as they're rounded correctly. If you're going to give me a decimal, please only put 2 or 3 decimal places. And I'm okay with percentages. They're all fine. Okay, awesome. Let's keep going since it seems like that one went okay. So now we're going to get into that next type of probability, which is called empirical probability, which was written wrong as experimental probability or something on the lecture notes, but it's empirical. So it's a little bit similar to the last, to theoretical, but it has a slight difference. So it's conducting an experiment and recording the results, and then it relies on actual experience to determine the likelihood of an outcome rather than assuming equally likely outcomes. So if you remember when we were talking about flipping a coin, we said, oh, you have an equal chance of getting heads and an equal chance of getting tails. This would be a little different. So I'm going to just jump down to this example just to read it. So the example here is toss a coin 10 times and record the results, and then use that to find the probability of getting heads. So instead of saying the probability of getting heads is 1/2, you would actually toss a coin 10 times, see how many times it came up as heads, and use that as the probability. We'll do an example with it as well, but this is just a little different because it uses results from an experiment as the likelihood of something happening. So it says, given a frequency distribution, the probability of an event being in a given class is P of E equals the frequency for the class over total frequencies in the distribution, which is equal to F over N. Make more sense once we do an example. So this is called empirical probability, and it just relies on results from an experiment instead of just assuming that outcomes are equally likely. Okay, so let's do this example here. So we're given this frequency distribution here, and it's on major field of study. And we're told that for math, we have the frequency of 5. So maybe we have 5 math majors. For history, we have 7. And for English, we have 4. And then for science, we have 9. And that's a total of 25. So we know 25 people and where they lie in terms of their major. So if I want the probability of being a math major, so that's going to be written as P of M. My empirical probability tells me that this is equal to the frequency for that class over the total frequencies in the distribution. Okay, so the frequency for the class being math, there's 5 people there, so this is going to be 5. And then my denominator is just the total number of frequencies, which is 25. So this is 5 over 25, which reduces to 1/5. So very, very similar to the empirical one in terms of you're, putting like the possible ways to get it or the amount of recorded ways over the total. So really similar in terms of how you find them. It's just one is using theoretical probability, which is, okay, we assume everything's equally likely, and one is using actual results. All right, so why don't you guys try doing the science one on your own and doing the probability of being a science major? You can private chat me your answer when you get it. So just do P of S, and I'll do history or English together as a group. And then just send me a chat when you have the probability of being a science major. Great. Okay, so I got like 4 responses, all of them correct, which is funny because I got all 3 types of responses. So I got one fraction as 9 over 25, which is correct. So I'll write that one down. This is 9 over 25. I also got 0.36, which is correct as well. And then I also got 36%. So it's funny, I got all 3 options, but they're all correct. So yes, good job, everyone. The next one I wanted to do as a group. So this is the probability of being a history or English major. So to satisfy this event, you can either be in history or English. So how that works is we just add together the 2 frequencies. So this is equal to 7 plus 4 over 25, because either history or English satisfies this, and there are 7 people in history, 4 people in English, so that's 11 over 20. Okay, any questions on this so far? All right, great. There's a thing here that says let's do an activity, and I'm gonna say let's not. So let's not do an activity. Okay. Next, we talk about this thing called the law of large numbers. I don't even think this is on your study guide. It's just more something to like understand and know. So I'm just going to read the definition and briefly like explain what it means, but I don't even think it's on the study guide. Okay, so let's go talk about this because this is kind of cool and something to understand. So the law of large numbers tells us that because of okay, there's like a blank. Okay, I'm going to explain it first. So the law of large numbers says that let's take an experiment, for example, and let's do tossing a coin. So if you toss a coin once, we say with theoretical probability that you have a 1/2 chance of getting heads. So we just say theoretically 50-50 chance you get heads or tails. But if you were to toss a coin 50 times, would you actually get heads 25 of the times? I mean, maybe, but probably not. There's a large chance that you probably won't get heads 25 times exactly. So even though theoretically we say, oh, the probability of heads is 1/2, most likely if you tossed a coin 50 times, you wouldn't get heads half the time. So what do they mean by round die? I know. In the example, let's roll a round die. Is it just like a sphere? Like I don't even really know what this was meant to say. So I read it and I was like, I don't know. So I I crossed it out. Some of the stuff I gotta cut out if I don't feel like it's that important. So I'm not really sure. I'm assuming by a round die, it just meant like a sphere. But does the sphere ever stop? Like I'm not really sure what this was intended to accomplish. So that's why I skimmed it. So to answer your question, I think it was just kind of like a sphere. Anyways, um, back to the law of large numbers. So, will you get heads 25 of 50 times? Probably not. But the law of large numbers will tell you that the more times that you toss a coin, the closer you'll probably get to half of it being heads. It's really interesting. So, the more times that you toss the coin, you'll get closer to half of the time it being heads and half of it being tails. So essentially, it kind of tells you the empirical probability. So when you do an experiment, eventually approaches the theoretical probability the more that you do it. And that's why it's called the law of large numbers. Because if you do it a large amount of times, the empirical probability that you're observing in your experiment will probably approach the theoretical probability. So if you toss a coin a bunch of times, you should get somewhere close to 1/2 of the times it's hit. So just something kind of cool to know. And then it says, because of the law of large numbers, we will interpret the probability to be the long run result, which we know approximates the theoretical probability. So there's something interesting. Like I said, I don't think that's even on the study guide, but it's just kind of cool to note the connection between empirical probability and theoretical probability. Okay. And then down here, it says the probability of a particular outcome is the proportion of times the outcome would occur in the long run. So, like it says, when we're doing, empirical probability or talking about it, we just assume it's kind of like in the long run. Okay. Now we can move on to the next type of probability, which you can see we don't really talk about it too much. It's got like 3 bullet points, and that's it. This is called subjective probability. And it says that it uses a probability value based on an educated guess or estimate, employing options and inexact information. So an example would be, what is the probability that you will pass this class? Not something that I can give you an exact probability for. I could not, come back to you with a number that would really represent your chance of passing the class. So that's just like a guess. Like I could look at you and say, right now there's like a 70% chance you'll pass, but that's just something I thought and came up with. I didn't like run any experiment. There's nothing that told me that it was 70%. It was just me making an educated guess. So that's another form of probability. Or maybe like, I don't know, like you go to the doctor and they're like, oh, there's a 20% chance you'll need surgery. You're like, where did they get that? Like, how 20%? What numbers did they run or think about to get 20%? It was just an educated guess. So that's subjective probability. We don't really do anything with it. It's just another type. And then it says you can read about probability and risk taking on page 160 or 196 through 197. So just a little added bit of information that you can read about in your free time. And that will wrap up section 4.1. That was a pretty long section. It's 5 pages. I know it's a lot because it introduces a lot of new things, but that is it for the first section. So any questions or comments before I move on to section 4.2? I just want to say that I think my experiment is going pretty well because I haven't yawned a single time as I've been drinking my coffee. So maybe we're seeing a correlation here between some variables. It's probably the worst thing I've said, but okay. Let's go on to section 4.2, which is the addition rules for probability. So there are times when we want to find the probability of 2 or more events. For example, when selecting a card from a deck, we may want to find the probability of selecting a card that is a 4 or red. So in this case, there's 3 possibilities to consider. And by red, the color being red. So, okay. So 3 possibilities to consider here. So one would be either I pick a card that's a 4. So if I want to know the probability of picking a 4 or red, one of my options to satisfy that would be I pick a 4. Okay. Another one of my possibilities to satisfy would be the card is red. So I pick something that's red. So what? Hearts or diamonds? And then another option is that the card is a 4 and red. So it satisfies both. So note that a card can be a 4 and red at the same time. So it brings up an interesting point because then you also have to think about two like events that maybe don't overlap at all. So the next one says, now consider selecting a card where we want to find the probability that the card is a spade or a diamond. So those don't overlap. You can't pick a card that is both a spade and a diamond. So that doesn't, like, there's no options that satisfy both at the same time. So when we consider our two possibilities, it's only either the card's a spade or the card's a diamond. You can't pick one that's both. So like it says here, notice that the card can't be both a spade and a diamond. So it can't satisfy both of these conditions at the same time. And this gets us into talking about different types of events. So two events, A and B, are called mutually exclusive or disjoint if they have no outcomes in common, which refers to our second example up there. And that really just talked about how a card can't be a spade and diamond. And because those events don't overlap at all, we would call those mutually exclusive. Means they can't happen at the same time, or there's no outcomes in common. All right, let's look at this example. So this example is rolling a die. An event A is rolling a 3, 4, or 5. And event B is rolling a 1 or a 6. So we would say that these are mutually exclusive because nothing in them is the same. So in event B, it's a 1 or a 6, and in A, it's a 3, 4, or 5. So if I roll my die, both A and B cannot happen at the same time. So nothing in A and B is the same. So we would say these are mutually exclusive. Okay, and then we talk about another, like the opposite of this, basically. And this is the intersection of A and B consists of outcomes that are in both A and B. And so you could say that A and B are non-mutually exclusive if there's things in their intersection. So let's look at this example. So example is rolling a dice and you let A be a multiple of 3 and let B be an even number. Okay, well, let's write down what that means in terms of the options. So if A is rolling a multiple of 3, that's really rolling either a 3 or a 6. And if B is an even number, that's really rolling a 2, 4, or 6. Okay, well, these events do have something in common. They both have a 6 in them. So if I roll a 6, I satisfy both events A and B because I've done something that's in both of them. So we would say that the intersection of A and B is 6. Because up here we define the intersection as outcomes that are in both A and B. So for A and B, the outcome of rolling a 6 is in both of them. And that would mean that we refer to these events, so they are non-mutually exclusive. Because they can happen at the same time. So we would say they're not mutually exclusive or non-mutually exclusive. We define the intersection as being events that happen in both A and B. And then we're also going to define this word called a union. And a union of A and B, it consists of all of the outcomes that are in A or B. So a union of something is all of the events in A and all of the events in B together. Oh, good question. So yeah, if you've heard of union or intersection before, you've probably seen like union written as, oh my gosh, sorry. You've probably seen union written as that and then intersection written as that. So because I'm familiar with them, if that's what you would like to write, you can definitely use that as your notation. But I am fine with you writing the words out. In fact, in all of my notes, we will just write it out. So we'll either say union or intersection, or you will see down below. Let me see if I can find it. So you'll see instead of that, we write A or B and A and B. So instead of doing like the U and the like, I don't even know, the upside down U, instead of doing those symbols, we'll just write or and. So if you are comfortable with the symbols, that's okay, but I'll just write words out to keep it simple. That's a good question if you've seen union or intersection before. Okay. So there's a little note here that's kind of interesting to think about. In probability, the phrase A or B denotes that either A occurs or B occurs or both occur. So you might be used to thinking of this or that as like one or the other. So A or B, you would probably traditionally think of it as it's either A or B. It's not both. But in probability, when we say A or B, that means A or B or both. So there's like an added in addition, I guess, to that. So just note that in probability, saying A or B can mean both. Okay, let's look at our example here. So it's rolling a dice. Let A and B be described as in the previous example. So we're going to roll a die, and A is going to be a multiple of 3, and B is going to be an even number. So let's find what is the union of A and B. So we already said that the intersection of A and B was 6 because that's the only thing that they have in common. But the union is going to be everything from A and everything from B together. So if I add these together, the union of A and B would be 2, 3, 4, and 6. So that's everything that exists between the two of them. So intersection is anything they have in common, and union is just taking everything in A and everything in B and basically just putting it together. All right, well, there's a reason that we talk about this. This gets into the addition rule. So it's important to understand the difference between the union or the intersection of events, because this is where we're going to discuss how to find the probability of a union of events. So this is known as the addition rule, and it tells you that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So let me kind of explain why logically this should make sense that this is how you find this probability. So if we want the probability of A or B, first of all, we're going to take the probability of A happening and add the probability of B happening. So remember, A or B can mean that A happens or B happens or both happen. So if we add together the probability of A and the probability of B, we've got those together, but we have to subtract out the probability that both of them happen, because if we don't, it's almost like we're double counting events. So the reason you subtract out their intersection is because you've already accounted for that when you've added the probability of A, the probability of B, and then you're going to take out their intersection because you don't want to double count for any events. So logically, that's kind of why that should make sense. But let's get into applying this. So let's do a example down here. Oh, and then a little note, the addition rule is used on single stage experiments, which just means one trial. Okay, so this example says, select one marble from a bag with 3 green, 4 red, and 7 white marbles. This is also a very common example you'll see is like selecting marbles out of a bag. I don't think anyone can come up with any more good examples because everyone uses the same like 4. So we're gonna pick a marble. So I'm going to describe an event here that we're going to calculate the probability of. So I'm going to say that my event A is picking a green marble. And then I'm going to say that event B is picking a red marble. Okay, and I'm going to tell you guys, let's find the probability of A or B happening. Well, let's find the probability of picking a green marble or a red marble. Okay, well, with my formula up there, this is equal to the probability of A plus the probability of B minus the probability of A and B happening. Okay, well, first of all, I need to figure out the probability of picking a green marble. So think back to the beginning when we were doing stuff like picking a card out of a deck, and we were just putting the amount of ways this can happen over the total possible outcomes. So first of all, let's note that we have 14 total marbles. Okay, well, the amount of ways that I can get a green marble would be 3, because in my bag, I have 3 green marbles. So I have 3 possible ways to pick a green one out. The probability of picking a green one is going to be 3, and then I have 14 total marbles, so it's going to be 3 over 14. My probability of picking a red marble is going to be 4 over 14, because there's 4 different ways that I could pick a red marble out. All right, and then lastly, I have to subtract off the probability of A and B happening. So if you really think about this, the probability of A and B happening would have to mean that I pick one marble out and it's somehow both red and green. That doesn't logically make any sense because I have 3 green and 4 red and 7 white, and there's no way I can pick a single marble out and get both green and red. There's 0 chance of that happening. So if you remember back when we said, if an event cannot occur, it has a 0 probability. So the probability of A and B happening is 0. Okay, so if I just add these together, I get 7 over 14, which is 1/2. All right, let's do another example here. So a deck of 52 cards and picking one card. Let's find the probability of picking a 9 or a diamond. Okay, so these are 2 events. So I have the picking a 9 or picking a diamond, and I want to know the probability of getting either of them or both. So based on my formula, this is equal to the probability of picking a 9 plus the probability of picking a diamond, and then minus the probability of picking a 9 and a diamond. All right, so the probability of picking a 9 out of a deck of 52 cards, there are 4 9s in that deck. So that probability is going to be 4 over 52. Okay, and the probability of picking a diamond, there would be 13 diamonds in the whole deck. So that's 13 over 52. And now I need to subtract out the probability of getting both a 9 and a diamond. But there's only one 9 of diamonds in the deck. So there's only one of them. So the chance of drawing a 9 of diamonds out is only 1 over 52. So I only have to subtract 1 over 52. And then this is equal to 16 over 52, which reduces down to 4 over 13. Okay, any like questions on this formula or how I applied it at all? There's a lot of formulas when it comes to probability. We're going to get into a lot more of them in the last 30 minutes of class. So, you get that formula sheet for your exam. So if you're looking at this and you're like, this is a lot to write down, write those down on your formula sheet. It's totally fine. I feel like if you can apply what I've given you, that's really when you know what you're doing. So if I can give you tools and you can apply them and you know how to use them, then I know that you know what you're doing. Okay. That's actually it for section 4.2. So 4.2, I think, is just on the addition rule. Yeah, the addition rules. So that's it. So this is just talking about the difference between a mutually exclusive event and then one that's non-mutually exclusive, and then you get into intersections and unions, and that's when you can talk about the addition rule. So you can see on my two examples, my first event, so picking a green marble and picking a red marble, A and B in this case are mutually exclusive because they can't both happen. So because they couldn't both happen, that probability of A and B ended up being 0. That's just a little thing that actually does happen. So when you're doing mutually exclusive events, the probability of A and B is going to be 0. And then down here, I had an event that was not mutually exclusive. So I could get both a 9 and a diamond with that one event. So you'll notice that then my probability of 9 and a diamond was 1 over 52 because they are non-mutually exclusive events. All right. This is the last section for the day. It is the multiplication rules and conditional probability. This has a lot in it, just a warning. So I'm going to get us some water first, and then we'll start. Okay, so with the addition rule, we talk about two events happening at the same time. And that's when we want to know what the probability of that is. But the multiplication rule is a little bit different. And the multiplication rule is used to find probabilities of two or more events that occur in sequence. So they occur back to back, not at the same time. So like with drawing a card from a deck, so what's the probability of getting like an ace and a card that's like a heart, or a card that's hearts. So those are like two events that can happen at the same time, where multiplication rules, we're talking about events occurring in sequence. So a little different here. So it says, in other words, when there are multiple stages in the experiment, two or more trials. So the last thing we talked about was one trial, and the multiplication rules are for two or more trials, so more than one stage. So an example would be tossing a coin and then rolling a dice. So maybe it's like, oh, you toss a coin, roll a dice, what's the chance of getting heads, and then rolling a 4. So it's two things that happen in sequence. So with two events happening in sequence, naturally we think about, are these events related at all? So two events, A and B, are referred to as independent if the fact that A occurs does not affect the probability of B occurring. So two events happening in sequence, and if A occurring does not affect B, then they are independent. They have no effect on each other. So an example would be tossing a coin and getting heads. And then rolling a die and getting a 4. So the reason these are independent is because if I toss my coin and get heads, it doesn't affect my chance of getting a 4 when I roll the die. So if I toss the coin and get heads or tails, that has no impact on whether or not I get a 4 once I roll the die. They do not affect each other. So then we have our multiplication rule for independent events. So the probability of the intersection of independent events. So that is given as the probability of A and B is P of A times P of B. Hence the multiplication rule, because you just multiply them. So when they're independent events and A happening has no effect on B, we just multiply their probabilities. So let's do this example. So it's rolling a dice and then spinning a spinner. So I'm going to draw for you what our spinner is going to look like. So say it looks like this. We'll say there's 4 possible things we could land on when we spin it, and that's A, B, C, or D. So we're going to roll a standard 6-sided die and then spin a spinner right after. So I'm going to call my event A. I'm just going to say it's rolling a 4. And I'm going to define B as landing on, let's do landing on B. So I spin the spinner and it's landing on B. Okay, so let's calculate the probability of A and B happening. So this is P, A, and B. All right, well, my probability, or this is equal to P of A times P of B. Okay, and then my probability of event A is just the chance of rolling a 4. My chance of rolling a 4 is just going to be 1/6 because there is one way to roll a 4 and there are 6 possible outcomes. And then my probability of landing on B when I spin my spinner is going to be 1/4 because we're going to assume there's an equal chance of landing on A, B, C, or D. So 1/6 times 1/4 just gives me 1/24. Okay, let's try the next example. I'm going to give you guys a few minutes to do this one, but let me explain some of the wording in it. So we have a deck of 52 cards, and we're going to draw 2 cards from a deck with replacement. So let me explain what this means. So it means basically I draw 1 card, and then you put the card back in and draw again. And the reason that we say with replacement is because we're trying to talk about independent events here. So we want to replace the card so that when we draw our next one, our first draw doesn't affect the second draw at all. So these are 2 independent draws of a card from a deck. So that's really common wording that you'll see is with replacement and without replacement. We'll get to without replacement next. But for this sake, just know that you're picking 1 card, looking at it, and putting it back in. So you want to draw 2 cards from the deck with replacement. I'm going to say event A is going to be, I almost wrote the same thing. So event A is getting a king. And then event B is going to be you get a 7. So I want you to find the probability of A and B happening when you draw the first one and then draw the second one. So go ahead and give this a shot with that multiplication rule that we learned. And then when you get an answer, same thing, private chat me your result. Okay, let's go ahead and talk about this one. This one was probably a little more challenging. Okay, so by the multiplication rule that we have up here, these events are independent because we replaced the card. So the probability of A and B is just the probability of A times the probability of B. Okay, well, my first event is just the probability of getting a king. So in a deck, there are 4 kings. So this is equal to 4 over 52. All right, and then my next event, B, is getting a 7. There are also 4 sevens in the deck, so my chance of drawing a 7 is 4 over 52. And all I do is multiply these, and that's equal to 1 over 169. Any questions on this one? All right, so there is one more example for these, but I'm going to go ahead and say try this one at home just because we do only have 18 minutes left and I still have a decent amount to cover. But if I don't finish it, I will just make sure that absolutely nothing that we didn't get to is on the exam. So I will make sure of it, but we might get through it. We'll see. Okay, so this next thing just says often 2 events are not independent. So it's really nice when we can assume that they are. So like on the last one, we drew a card from a deck and we replaced it, which means that our events are independent because we start fresh with the same deck. But sometimes we have dependent events. So when the outcome of one event will change the probability that the other occurs, then we say we have dependent events. Okay, so an example of this would be, sorry, picking a card from a deck, not replacing it, and drawing a second card. So that is an example of something that's dependent because I take a card out, I don't put it back in, and then I draw another one. So automatically those are dependent from each other. Depending on what that first one I took out was, that changes my probability of the second event happening. So right down here it says, when events are dependent, we cannot use the current form of the multiplication rule, and we have to slightly modify it. So then we get the multiplication rule for dependent events. So in this section, we have a multiplication rule for independent and one for dependent events. So when 2 events are dependent, the probability of both occurring is the following. And you're seeing for the first time this really interesting like symbol / form here that is very foreign, but it's defined at the bottom of the page, and it's known as the conditional probability. But I'm going to just write up here, this is the probability that, or sorry, the probability of B given that A occurred. Oh my goodness. There we go. Okay, so that's what that little symbol and notation means. So if your events are dependent now, instead of just multiplying the probability of A times the probability of B, now we have to do the probability of A times the probability of B, but it's given that A occurred. So because we know that if A occurs or not, that is going to affect the probability of B, we have to account for it. So now we have to say, okay, this is no longer just A, or probability of A times probability of B. Now it's the probability of A times the probability of B, but given that event A occurred, because that will have an impact. So let's kind of do an example and see why this is true. So this one right here is drawing two cards without replacement. Like I said, those are very key terms that you'll see in probability with cards is with or without replacement. As soon as you see without replacement, these are dependent events. And as soon as you see with replacement, these are independent. All right, so we want to find the probability of a jack and a 2 in that order. So we want P of J and 2. Okay, well, we're doing them without replacement. So these are dependent events. So according to my formula up here, this is P of J times the probability of getting a 2 given that we got a jack. So this is read as the probability of getting a jack times the probability of getting a 2 given that we drew a jack on the first one. All right, so the first part is not too difficult. The probability of getting a jack, we've done this multiple times. So there's 4 jacks in a deck. And so the probability of drawing a jack will be 4 over 52. So that one, that's pretty standard. We've done that. This next one is where you really have to think about it. So the next part that we're filling in is the probability of drawing a 2 given that we drew a jack and we did not replace it. So let's think how this affects our probability here. So if I took a card out of the deck and I didn't put it back, the first thing that really comes to mind is that the denominator here is no longer 52, because on my next draw, there's only 51 cards in the deck because I took one out and I didn't put it back. So this denominator becomes 51 because I no longer have 52 possible cards to pick. I only have 51. Let's say I drew a jack and I didn't put it back. So there's only 51 cards now in the deck. But that's the only thing that it changes because my numerator is still like all the ways that I can get 2, and there's still 4 2s in the deck because I drew a jack. So that doesn't change the amount of 2s in the deck. There's still 4 2s. The only thing that it changes is that I no longer have 52 cards in the deck. I only have 51. So when you're doing the conditional probability and you're thinking through this, just think, how does that first event happening affect the chance of that next one happening? So if I just multiply these across, this ends up giving me, in reduced form, 4 over 663. Let me double check that. Yeah. All right, let's do another example just to really like get some practice with the conditional probability. So this is selecting 2 marbles from a bag with 4 pink marbles, 1 green marble, and 3 red marbles. And we're going to make a selection without replacement. Okay, so I'm going to say that we want to find the probability of getting a pink and a green marble. So we're picking 2 from the bag, keyword without replacement, which makes this dependent. So I want the probability of picking a pink and then a green marble when I don't replace the pink one back in. I don't replace the first marble that I pulled back in. So based on my formula, this is equal to the probability of getting a pink marble times the probability of getting a green marble, given that I drew a pink one. All right, well, the probability of getting a pink marble, let's see how many marbles there are total. So 4 plus 1 plus 3 is going to get me 8. So there are 8 total marbles. So my probability of pulling a pink one out, there are 4 pink. So I have 4 ways to pull a pink one out, and I have 8 total marbles. So there's a 4 over 8 chance of getting a pink one. And then my next probability that I have to fill in is the chance of getting a green marble given that I got a pink one out the first time. This is really similar to the card example. So I pulled a pink one out and I didn't put it back in. So now what's my chance of getting a green marble? Okay, well, this doesn't change the fact that there's still one green marble in the bag. That one's still there because I pulled a pink one out. But what it does change is that because I took a marble out, there's no longer 8 marbles in the bag. There's now only 7. So it changes my total amount of marbles in there. And then I multiply these across and I get 1/14. Okay, any questions on the multiplication rule when you're dealing with dependent events? Okay, so I think I'm just going to try and do the next example, which discusses conditional probability a little further. And I will probably have to cut out the last part, which is the probabilities for at least. So I'll probably have to say that's not going to be on the exam, that at least probability. So let's just try and get through the conditional probability examples, and then we can stop there. Okay, so for events A and B, the conditional probability, so remember that's the probability that B occurs given that A occurred. That's equal to the probability of A and B occurring over the probability of A occurring. So I warned you there were a lot of formulas with probability for different types of events or scenarios. So this is just another one. It's a conditional probability formula. So whenever you're asked a question like, what's the probability of this given that this occurs? Conditional probability. So anytime, I think the key word is really given, or, if you see what's the probability of this when this happened before it, conditional probability. All right, so let's do some examples here. So this is called a contingency table, just so everyone knows. This just gives you some, like, I think of the best way to describe this. It's kind of like a frequency distribution almost. So how it tells you how often something occurs, it's kind of similar. So like this is kind of a funny example, but the questions are about Cooper's roommate and if you party and like snoring. It's just like a really interesting example, but whatever. So like this table tells you right here that there's, let's see, 150 people who party and snore. And right here, there's 200 people who don't party, but they do snore. And that's a total of 350 people that snore. So that's like how to read one of these tables off. So like this one is 100 people who don't snore and they party. And this is 550 people who don't snore and they don't party. So total, that's 650 people who don't snore. And then same this way, this is 150 people who snore and party, 100 that don't snore and party. So this way you get 250 people that party. So that's how you read one of these tables off, and they are helpful when you're doing things like conditional probability. So let's try and do this example and this example, and we'll probably stop. Okay, so find the probability that Cooper's roommate will be someone who parties given he snores. So remember I said keyword given. So when you see the word given, it's a conditional probability problem. So what we're looking for is the probability that his roommate will be someone who parties given that he snores. So I'm just abbreviating parties to P and snores to S. And using our formula up here, this is equal to the probability of P and S. sorry, I should have written S and P, doesn't really matter, but to stay consistent with the formula, over the probability of S. Okay. So let's find each of these pieces. So my numerator is the probability of S and P. So this is the probability that someone parties and snores. So we have to figure out what the chance of that happening is. So if we come onto our table and we come across from the party column and the snore, or party row and the snores column, there's 150 people here that do both. And this is out of 1,000 total people. So the probability that someone snores and parties is going to be 150 over 1,000. Because there's 150 of them, and of my sample, I had 1,000 total people. Okay. Next, I need the probability of S. So this is just the probability that someone snores. Okay, well, I have 350 total people that snore over 1,000 total. So this is equal to 350 over 1,000. All right, now I just have to plug these into my formula. So this is 150 over 1,000 divided by 350 over 1,000. And this is equal to 150 over 350, which is equal to 3/7 or 0.43. The probability is a lot of using the formulas that you're given and plugging in the pieces. So trying to find the pieces of the formulas and plugging them in with the information that you're given. So the next part isn't too bad because it's find the probability that Cooper's roommate will party and snore. And we found that in our process of finding part A, first of all. So we had to find the probability of someone who parties and snores already. Okay, so I think this is very, very, maybe I'll just try to do this example. I think I can do it. Probably. Let's see if I can do this one and then we'll be done for today. So one more example of conditional probability. So the probability that Cooper parks in a no parking zone and gets a parking ticket is 0.09. And the probability that Cooper cannot find a legal parking space and has to park in the no parking zone is 0.20. Today, Cooper arrived at UCD and has to park in a no parking zone. Find the probability that he will get a parking ticket. So first of all, we know that he had to park in a no parking zone. And we want the probability that he will get a ticket given that he had to park in the no parking zone. So down here, we've defined N to be parking in a no parking zone and T to be getting a ticket. So really what we're asking is the probability that he gets a ticket given that he had to park in the no parking zone. Okay, well, based on my little formula, this is the probability of, oops, oh no, that's right, probability of T and N. Sorry, I'm trying to stay consistent with the formula here. So N and T over the probability of N. But we're given both of these probabilities in the problem setup because we know the probability that he parks in a no parking zone and gets a parking ticket is 0.09. And we're told the probability that he can't find a parking space and has to park in the no parking zone is 0.20. And if you just divide these two, you get 0.45. So it's just a matter of filling in the information that you're given into the formulas that you have. So I am not going to do the at least probability, even though it's only one example. I'm not going to do it. Don't worry about it for the exam. I will not put anything on there that is a probability that says at least. So don't worry about that. We'll do it. We'll do it before the exam, but it won't be on there. So don't worry about studying that. But everything else is fair game on here. So I will stop talking. If you have any questions on the project or the exam, feel free to send me an email. Unfortunately, I can't hang out after class right now to talk about it. If you have questions, send me an email or text me on that Google number and I will get back to you. So please reach out if you're studying and come across anything. Yes, 1 second. Sorry, there's a chat. Okay, so you guys are now free to go.